introduce yourself to us, please?
Yes, thank you. Do you see the screen?
Yes, we can see it.
Okay. Well, in this conference, thank you very much for the invitation. In this conference, I remember when I stayed in Turkey around 2012, and I met Mustafa Karer. It's amazing travel to Turkey in these days. So thank you very much for this invitation. And I am Ivan Campos Silva, and I'm working in the National Polytech Institute in Mexico. Here's my group. I'm working in the surface engineering group in Mexico. So I want to talk about a novel and alternative method to produce surface layers on different metallic materials that our group called Pulse DC powder pack boriding process. The presentation is made by one of my students, Eric Jafet Hernandez Ramirez. So we start the talk, yeah?
Okay.
This is the outline of my presentation. This is an introduction, a methodology. I want to talk about also with the kinetics of different models applied to different boriding materials, the conclusion of this talk, and finally the reference that I use for this presentation. Yeah. Well, if you know the powder pack or the boriding process is a surface diffusion process that when the boron atom diffuse into a metallic surface and produce hard iron boride layers or cobalt borides or nickel borides at the surface of different metallic alloys. In this, there are different methods used for boriding process, like salvat, powder pack, that is in the talk about I talk in this conference. Also, we have a gas phase boriding process, and finally the plasma process. There are different methods, but in different ways we can use these methods concerning principally to the equipments that we use in different laboratories. In this case, I show you different metallic borides formed at the surface of metallic materials. For example, in low carbon steels and high alloy steels, and also an Inconel 718 alloy, and finally with medium carbon alloys. In this case, we can see different types of morphologies at the surface of materials concerning to the formation of the boride layers at the surface of the material. For example, it's a jagged structure depending principally in the of the alloy and of the elements of this substrate, and also this jagged structure formed on the surface. We also it's also changed depending in the content of the alloying elements in the substrate. So basically, I want to talk about the principle. Initially, I want to talk with the powder pack boriding process. It's a conventional process that the sample is embedded in the container, in a metallic container, and the container is hermetically sealed and containing the sample, and the sample inside the container are surrounded with a powder mixture, basically with boron carbide or also silicon carbide. It's a powder mixture principally, and also with an activator that promote the diffusion of boron into the surface at different temperatures. Traditionally, the temperatures are around 10, 111, 23 kelvins to 1273 kelvins at temperatures around 2 hours to 12 hours of exposure during the treatment. And also when the treatment is finished, the container is put out of the muffle and also cool slowly at room temperature. In this case, we can show the schematical representation of the boride layer during this powder pack treatment. And what is the disadvantage of this process? One of the principal problems is too much energy consuming because of the high temperature of the process and long exposure time, in addition to high consumption of the powder mixture. For these reasons, several works have developed an alternative process to reduce the exposure time and for the formation of the boride layers on the surface of ferrous and non-ferrous alloys, and to raise the mass transport during the powder pack boriding process, in this case, with the aid of the direct current field. In this case, we can see, for example, let me see here, okay. This is a traditional powder pack boriding process with the aid of a direct current field. Initially, we can see a setup of the equipment. This is the sample that are collocated between two electrodes that are connected to the power supply at the top of the container. The sample are embedded in a powder mixture, and during the process, principally during the process, we generate electric current during the process. The direct current, the electric current generates thermal and chemical effects that enhance the chemical reaction of the powder mixture and increase the number of ionized atoms at the material surface. At the same time, the current that flows here between the electrodes follows the direction of the conventional current, in this case from positive to negative, and generating an electromigration effect of the boron atoms, thus accelerating their mobility to the point effects of the materials. However, the migration of the ionizing boron atoms on the surface exposed to the cathode, in this case, we can see in figure 5, two sides of the material exposed to the direct current field. We have, in this case, here, the side facing the cathode and the side facing the anode. So we have the similar boride layer thickness at the surface of this material. For example, in this case, we talk about the cobalt alloy. So if you see, there is a difference between the layer thickness, and to the application of the materials we can fail, and we have different materials properties at the surface of this material. So in the case, we can see that the direction between the boron atoms is opposite in the normal direction of diffusion of the boron. So the growth of the boride layer is lower compared to the surface exposed to the anode. Well, here we can see propose a modification of this process. Consider an alternative method that denominate pulsed DC powder pack boriding process. This method is an alternative of the direct current field, but in this case we can use in the schematic representation, we can use in the same way as two cathodes that are where the specimen are collocated between these electrodes, between these electrodes, cathode and anode, a power supply that are connected to the container and also with the electrodes that we use in the process, and a control device. This control device are used to change the direction of the boron atoms at the surface of the material exposed to the direct current field. So initially, we can use For example, in the first time we use this is the normal diffusion of the boratoms at the surface of the material. So the device control here change the polarity of the electrodes. So the boratoms change the flow directly from the surface of the material. And then this polarity change, we can modify around 10 seconds, 5 seconds, 20 seconds. And also the modification of this polarity change during the process also influence in the growth kinetics of the borided layers. So it's very interesting. Also, another novel from this method is to reduce the exposure time and the temperature of the process compared with the traditional or conventional powder pack boriding process. So it's a good idea because the energy consumption during the process is reduced, and also the powder mixture used during the process is more efficiently during the process, and we don't have waste about this powder mixture during the process. And also the effect, we have two effects during the process. First, the electron migration of the boron atoms to the surface of the material, and also the energy activation of the boron atoms in the formation of the borided layers are also reduced. So we have some examples about this process concerning the works of my students. I suppose that are here. Thank you very much for my students that also wake up early in the morning today. But in this case, we have a schematic, also the representation of the boron diffusion during the pulse DC powder pack boriding process. Firstly, you see we have the substrate, also the ionized boron atoms that diffuse toward to the substrate. The effect of the current field during the process promotes the generation of punctual defects or the increase of punctual defects during the process, principal vacancy. Also, we can also promote the generation of more interstitial positions in the lattice of the substrate during the process. And also, these boron atoms occupy the vacancy produces during direct current field during at the process. And also, and we can, during the exposure time, we also generate at the surface a reaction layer that consists of boron compounds at the surface, especially or related to the composition of the substrate. We have a double phase layer or a monophasic layer at the surface of the material. Also, if you increase the current, the direct current field during the process also generates more vacancy sites at the material substrate. Here are some examples that we performed, and I want to show you for this presentation, and performing at different substrates. In this case, it's high medium alloy, AIC 14140 and AIC 1018 steel, exposed during the process with a concentration of the power mixture that I show in the figure. In this case, we use a low temperature around 1073 kelvins with 900 and 2070 seconds. And we can show you that the two surfaces exposed to the process. In this case, we reduce the exposure time during the process, and also we use a direct current around 5 amperes. This is also another examples for this process. for a different steel. It's a speed alloy or uses in the manufacturing process, and also with the Amberco iron material exposed for this process. And also we can see that the formation of these layers are homogeneous because the diffusion of boron during the process related to the change of polarity during the process produce a uniform boride layer at the surface with a similar thickness on the material. Also, we can see another examples. This is principle. We can show that the process produce a little exposure time, a thick layer. In this case, the layer is principally related to the alloying elements of the substrate. We can see two types of layers at the surface of the material. Iron boride, for example, and a deboride layer at the surface of the material. We can also produce a mono layers in both sides of the material exposed to direct current field. And also this formation are related also with the composition of the power mixture, the temperature, and the exposure time. Also, it's important to produce a good layer substrate systems. So in this case, in figure B and C, we can also show that the microstructure of the substrate are modified with martempering and an austempering process. Also, if you see, this is very interesting, this result, because during the process, we change the polarity cycles for 10, 20, and 30 seconds. And we can also show that about these parameters that influence the growth of the layers. If you increase the polarity cycles during the process, the growth of the layer also increase. I suppose that is related to the charge of the current that is increased about the diversity of the cycles during the process. So we can also study right now the influence of these polarity cycles during the process to evaluate the kinetics of different borided materials. This is another example with another type of steel, 8620 steel, exposed to the same process. And also, we also see that the effect of the polarity cycles during the process. So it's very interesting, but because in short times, we can also produce a thick layers at the surface of the material. Well, in the methodology, principally also, I suppose that also know that the preparation of material are related by different procedures during the process to after and during and before the process, principally the preparation of material and metallographical preparation, implementation of the treatment, considered different temperatures, different exposure times, and different composition of the powder mixture. Also, the optical inspection of the surface to reveal the microstructure of the surface and the microstructure of the substrate during the process. And also, we can perform post-heat treatments after the process to reduce the fragility of the layer to the substrate and increase also and improve the adhesion between the layer and the substrate. Also, we can reveal the nature of the phases formed at the surface by X-ray diffraction tests. And finally, we can also implement different diffusion models to evaluate the kinetics and compare these results with our novel method to the conventional process implemented in the in different research and also in the industry. Okay, this is the two types of layers that I published this work in this year in the Surface and Coating Technology Journal. We can see two types of materials, stainless steels, and also develop at different conditions. 1123 kelvins with 1 hour of exposure and 1223 kelvins with 2 hours of exposure. And it's very interesting, the results, because in a low time with 2 hours, we can produce thick layers at the surface with good stability, with good mechanical properties along the layer substrate substance. We can produce also two types of layers in the surface, diboride and iron boride layer, with beneath the layer a diffusion zone consists of chromium-rich layer and a nickel-rich layer that support the mechanical performance of the layer concerning to the substrate, and they reduce, in this case, the diffusion zone, reduce the hardness and the young modulus gradient along the layer substrate system. Also, we can see another type of material. This is an Inconel 71 superalloy in this different condition of the process, and also produce a mixture of nickel borides at the surface with a deep diffusion zone below the top surface or the top layer. And also we can reveal different types of nickel boride layers at the surface, a mixture. Then also we can evaluate the kinetics during the process of these two types of materials. Well, in this presentation, I want to talk briefly about the models that we use during my research about this boriding process. It's a good model that produces a good results concerning the kinetics of the layers. The model considers basically a boron concentration profile along the depth of the boride layers, linear concentration, linear boron concentration along the layers, and also we can show the two mass balance equations concerning to the growth of two types of iron boride layers at the top of the surface of different borided steels. And the solutions of this mass balance equation are related, that we consider that the layers obey the parabolic growth law that is shown in equations 3 and 4, and also consider that the layers have an incubation time during the process. So in this case, it's important to mention that the growth constants are related to these parabolic equations. And finally, the final form of this equation is to obtain the boron diffusion coefficients of two types of layers produced by this novel method. This is the expressions that we use to mathematical expressions, a simple mathematical expression to obtain the boron diffusion coefficients. And also the model are fit with experimental conditions and the layer thickness obtained during the process. Well, here is some very interesting results. And in figure 16, we show the evolution of the layers versus the exposure time during the process. And the results of these experimental values, we obtain the growth constant with this behavior, a linear behavior. We can obtain the growth constant, and also these growth constants obtained experimentally, we use to obtain the boron diffusion coefficients. The boron diffusion coefficients are also expressed in a Arrhenius relationship that we show in this plot. And it's very interesting, the results, because we compare in table 4 the activation energies of boron in the different phases formed in different materials and compare with different results obtained by different researchers related to conventional powder pack boriding process. In this case, we can see that with our novel method, the energy activation for the formation of this kind of layers are reduced drastically compared with the conventional process uses in the industry or in different laboratories. So we are expected to continue this research, because we also evaluate this condition only with two types of current that are 5 amperes and 10 amperes during the process. Also, we can modify the distance between the electrodes and the sample. We can also change the current generated during the process. We can also change the polarity changes during the process. So it's a multivariable procedure that also we can obtain interesting results during the process. Here is, for example, when I mentioned the two types of current uses during the process for a stainless steel. And also you can see that the difference between the first micrograph, a cross-sectional view of the same materials, originated from two different current uses during the process. And also you can see that the difference of the boride layer thickness produced during the process. In this case, also we can increase a little to the exposure time to 2 hours of exposure, and also see that the effect of the current field during the process that increased drastically in a short time the boride layer thickness at the surface of the material. Also, we can see that the microstructure of the material also consists at the same architecture from the conventional powder pack boriding process, with 2 layers at the surface, the iron boride and diboride layer, and a chromium-rich layer beneath the top sulfur layer, and a nickel-rich layer at the end of the beginning of the substrate. Also, we can use another alternative diffusion models to reveal the kinetics of the material of the layer with the same assumptions that we considered in the last model that I showed you. That we use this model to publish an article. Consider this model that is mentioned that is a solution of the second Fick's law. The model is named mean diffusion coefficient, and also this model of the principal work of this model is to obtain the boron diffusion coefficient, also with the solution of the model concerning to the parabolic growth law of the layers during the process. Here's an example. We consider also the boron concentration along the depth of the layer, and also this concentration are used also to obtain the boron diffusion, and the growth constant named K1, K2 is obtained directly from the experimental condition and the measure of the boride layers during the process or after the process. And also we can see the difference between the process. The growth constant that I show you here shows that diffusion is a controlled process, and it's a good perspective of the process. We produce, if you increase the temperature or you increase the exposure time, also the growth of the layer are in the same way, and also it's a good aspect of this process. And also we can use this growth constant to reveal the to obtain the boron diffusion coefficients and also to obtain the energy activation of boron in the layers according to the Arrhenius relationship. Here's the difference that I mentioned, the effect of the current field with the activation energies. So it's very interesting because if you see in table 8, the reduction of energy consumption during the process, the treatment used 25% more electricity compared with the powder pack boriding process, and also with the Pulse DC powder pack boriding process compared with the current field performed during the process, 5 amperes and 10 amperes. The treatment reduced 33% electricity compared with the conventional process, and 65% electricity concerning the conventional boriding process, powder pack boriding process. Well, this is some conclusions. This is some results that we obtained in the last 1-2 years around about this process. So we can expect to in the same way to expect to have some more results considering the different variables obtained during the process, and to optimize the process concerning the formation of the layer during the process. This is my reference uses in this work. And finally, thank you for your attention. I am very happy to be here with my college, with my Turkey college, and especially I want to appreciate the support of Mustafa, my friend. Thank you, my friend. I remember you
Yes.
from my visit to Turkey around 2012. Thank you very much, my friend. Thank you very much for all. Thank you.
You're welcome. You are also best friend with me too. Also, thank you very much for your presentation. And actually, it's a very novel process for when we compare it to traditional boriding process. It's very interesting, especially reducing energy consuming. However, I have a question about did you perform the pulsed DC pack boriding samples? Did you perform Beer performance of the samples? Did you compare the conventional boriding process samples with the novel process?
Yes, if you see in the presentation, we can reduce the activation energies compared with the conventional powder pack boriding process around 65% compared with the conventional process. Yes, it's a good result. It's a very interesting results, and also we can also modify the activation energy of boron during the process using different variables during this novel method. So it's a long research with this alternative method. So we expect to have some results in this year about this process.
Okay, thank you very much. We have a question from Ali Günen. He is professor at Iskender University. You can read it also. I can read it, this question. Professor Silva.
Yes,
Ali Günen asks, yes, please.
Yes, you read me, please, because I don't see the question of Ali, please.
Dear Professor Camposova, maybe a bit off topic. What's your opinion on boronizing refractory type high entropy alloys?
Yeah.
Which temperatures, which environment, argon, helium, etc., and the boron powders to be used, amorphous boron, boron for carbide, etc., should be? We were able to boron high entropy alloys easily, but couldn't achieve satisfactory results in refractory type.
Yeah.
Molybdenum, niobium, titanium, titanium, and zirconium, high entropy alloys. I care about your suggestions because you are one of the world's leading scientists in the field.
Thank you very much for your opinion. I suppose, Ali, that it's possible to boride this type of materials. And also we can use this alternative method if you want. If you want a collaboration with this type of materials with high entropy alloys. You say that you use amorphous. Yes, I suppose that we can use powders assisted with a direct current field, and also we have temperatures. I suppose that the temperatures are too high because in the last years, one of my students stayed at Argonne Laboratory with Professor Ali Erdemir, and my student borided the molybdenum alloy with an alternative method that Professor Erdemir and Professor Cabezoglu use, that they denominate ultra-fast boriding process. So I suppose that these two types of process can we use to boride these molybdenum alloys on high entropy alloys. Consider principally and consider the content of alloying elements in the substrate. It's important to use high temperatures, that the container are very hermetically closed, and also if you with a specific powder mixture composition to obtain a good formation of the layers at the top of the material. So I suppose that is possible. So if you like to consider this method, you can send me the samples, and we can to our laboratory, and we can also produce this type of alternative layers in this kind of high entropy alloys.
It's good. In my opinion, it's very chance for us.
You have my email if you want to call me, and we can.
Dear Ali Günen,
This method to your high entropy alloys. Thank you. Yes, possible. You have 1273 kelvins for 6 hours. This is possible. Yeah. Yes, it's possible. Yeah. If you have results, you can call me, and we can have another alternatives to produce this kind of layers. Thank you.
Okay. Thank you very much. Also, do you have any question, dear participants, dear guests? No. Yes. Ali Günen say to you, thank you for your valuable.
Thank you, Ali. Thank you for your comments.
Okay.
I work with Ali. I work with different papers that we use in my works. Ali is a very good research in these topics of boriding. And thank you, Ali, for your comments.
Okay. Okay. There's not any question. Thank you very much for your participation, and it's very nice. It's very interesting presentation. Thank you so much, Professor Ivan Campos Silva.
I saw another question about with Mauricio Olivares. Is one of my students. I don't know. Yeah. Yes. 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 It's a conductive element. If you don't have in the power mixture the potassium fluorborate, we cannot produce the the electric field during the process. So it's important to consider the potassium fluorborate during the process because it's the conductor during the process. It's around 5. Yeah. No, it's only if you have around 5%, it's okay, no problem. Yeah. Also, you can use more content, and also the promotion of the ionizing atoms during the process also increase, and the discomposition of the power mixture is also increased during the process. No problem. No. Only this the promotion of the of vacancy and punctual defects in the substrate also only increase the diffusion, the boron diffusion on the substrate, on the surface of the material. Yeah, also, and the constitution of the layer are in the same way that we are obtained in the conventional boriding process. Yeah. No, thank you for you. Thank you. You're welcome.
Yes, is there a question? Okay. Thank you very much, Professor Silva. Actually, it was nice to see you again. I hope next time. Thank you. I hope we can meet. We can join next time.
Yes, you can come to Mexico if you like. Yeah?
Inshallah, I hope.
Yeah, no problem.
I will come there. I hope
Yeah.
next time we also invite you to Turkey and to Konya.
I have a great remembrance of Turkey, especially of Karabük.
Yeah,
it's a great city in Turkey. It's a special city, and I have a good remember about my stay in Turkey. Thank you very much.
you're welcome. You're welcome. Thank you very much for your participation. Dear participants, this plenary session